Welcome to qnawire.
So now we'll work on problem 98 from chapter 20. In this problem, we're told that a common shorthand way to represent a voltaic cell is we write anode, single line, anode solution. Then we have a double line to represent the salt bridge or the permeable barrier. Then we have cathode solution. And finally, the cathode. So a double vertical line represents a salt bridge or a porous barrier. A single vertical line represents a change in phase, such as from solid to solution. In part A, they ask us to write the half reaction and overall cell reaction represented by this cell, which they're given, and calculate the standard cell EMF. So in this cell here, we have iron, iron 2 plus, double line, silver plus, and silver. So now we can write the two half reactions. First, we can write the reduction, which is going to take place at the cathode. So we have silver plus, plus 1 electron, producing silver. Then we can write the oxidation reaction where we have Fe going to Fe2 plus 2 electrons. And the reduction potential for the silver reaction is 0.80. And for the iron reaction is negative 0.44. So to write the overall cell reaction, we can add these up here. We're going to need to multiply silver times 2 to balance the electrons. So we get iron plus 2 silver plus will produce 2 silvers and iron 2 plus. And then to get the standard EMF, we simply add or subtract these values, 0.80 minus 0.044, 0.44, and we get a value of 1.24 volts. So in part B, the cell which we're given is a zinc and hydrogen. Zinc is the anode and standard hydrogen electrode is the cathode. So first, let's go ahead and write what they give us. They give us zinc and zinc 2 plus. Then they give us H plus and H2. So first we can write the reduction reaction, which will take place at the cathode. So we have 2 hydrogens plus 2 electrons going to produce H2. And the oxidation reaction is zinc going to zinc 2 plus and 2 electrons. So the standard reduction potential for the hydrogen reaction is, of course, 0, since it's our standard. And for zinc, it is negative 0.76. So now we can write the whole reaction. We have zinc plus 2 hydrogen ions producing zinc 2 plus and H2 gas. And our standard EMF value will be equal to 0 minus 0.76. So it will be 0.76 volts. So now we can move on to part C. where we're given a reaction. Here we have ClO3 plus 3 copper, 3 copper solid, and 6 H plus. And this is producing chlorine, 3 copper 2, and 3 water. So this is the reaction that we're given. And we're told to represent the cell based on the following reaction, where platinum is used as the inert reaction, and they give us the standard EMF for a half reaction involving chlorine. So first we can write the cell. First, we can see that the oxidation is occurring with copper. Copper is being oxidized from copper 0 to copper 2. So we can start our cell by writing copper, single line, copper 2 plus. Now the question is, on the other side, what is being reduced, and what's in solution, and what is the cathode? And so we can see that the ClO3 minus is our reactant, and chlorine minus is the product. So at the cathode, usually the reduction is taking place from the cathode to the cathode solution. So we can follow the same pattern here. We will put the reactant as the solution and the product as the cathode. So we're given the reduction potential for this chloride reaction, which is 1.45, and we subtract this copper to copper 2 reduction potential, which we can find in Appendix E as 0.34, and it gives a value of 1.11 volts.